Training Tuesday. This topic is hydronic system balancing, which is my favorite topic of all of the presentation Training Tuesdays that we're doing. So I'm excited to cover this and go over it. We're going to be talking about hydronic system balancing, but in general, domestic water applications that have balancing issues, the same principles apply there as well. But as a rule, we're going to be talking about hydronic system balancing. So we're going to talk about why is system balancing important, and then the fun part is why hydronic systems are inherently out of balance, and then how you can use automatic flow limiting valves to maintain accurate system balance. So we'll start with the definition of a balanced system from the ASHRAE handbook, and their definition is a balanced system in waterside terms can be defined as one in which the terminal unit flow rates are adequate under design circumstances to maintain satisfactory heat transfer capability. So that is a very fancy way of saying that basically a balanced system, each coil, each zone in that system has the right flow at the right time so that you have the correct amount of heat transfer. So like we talked about in our last week's Training Tuesday, we talked about the automatic flow limiting valve and how David Griswold in 1960 saw a problem in the HVAC industry where hydronic systems were unbalanced. So that meant that some coils had too little flow and some coils had too much flow. So that is what is meant by an unbalanced system, is the coils don't have the correct flow to their design. And so in 1960, David Griswold designed the automatic flow limiting cartridge to address that situation of an unbalanced system. So it's been known for years that hydronic systems without any kind of balancing valves will have overflow and underflow, and so therefore it's an unbalanced system. So why is system balancing important? Well, we talked about a little bit last week about how the delta T, so the temperature drop across any heat transfer equipment, how that delta T is impacted by what the flow rate is. And this graph really shows in a graph form what we talked about. If you look at the graph, you can see that the heating coil is, a typical heating coil is the red curve, a typical cooling coil is the green curve. So if you're looking at a heating coil, as you increase your flow, so as you move along the x-axis and increase the percent of design flow rate, you increase the percent of design heat transfer. But you have the biggest impact on that percent of heat transfer in the beginning of a valve opening. So the beginning of the valve opening where you've got the percent of design flow is low, you have actually bigger heat transfer. And that makes sense. Last week we talked about our BTU per hour equations and how if you have the flow moving slower through a pipe, through a hose, through something, and that hose is subjected to either heating or cooling, you're going to get more heat transfer. So we talked about a hose in the sun. If a hose in the sun has low flow, you're going to have more delta T, more heat transfer across that, as opposed to when the flow rate increases. So this graph here shows how important it is to control the flow, and that you're controlling the flow so that the coil has the design flow rate that the engineer specified. So the engineer, when they're picking the coils, they have specified based on the room's basic principles, whether it's south-facing or north-facing, how many computers, how many light bulbs, how many people are going to be in it, what kind of loads it's going to see. That engineer has designed that coil to a specific flow rate, and so there needs to be some kind of controlling of that flow rate to really impact the heat transfer in the system. So why is balancing important? Well, the first would be low flow problems. An unbalanced system, like we talked about, an unbalanced system means that in the coils, typically farthest from the pump, you've got low flow. You don't have enough flow. And in the coils closest to the pump, you have too much flow. So in an unbalanced system, a building manager can get a complaint on the same day for too much heating in one room and too little heating in another room. And that would be an unbalanced system. So the low flow problems are typically the coils or the units that are the farthest from the pump. And so you've got hot and cold spots when there's low flow. You can have short circuiting and equipment malfunctions when there's low flow. That would be primarily in something like a heat pump, but in anything where you don't have enough flow at the end of the run could cause short circuit and equipment malfunctions. One of the main issues with low flow is tenant dissatisfaction, where you get complaints from tenants that they don't have enough heating or cooling because there's not enough flow to those zones. And that therefore leads to increased number of callbacks. So low flow problems exist in an unbalanced system, and typically they are in the ones that are the farthest from the pump. The exact opposite can occur in the same exact system if it's unbalanced, where you have high flow problems. So typically the units closest to the pump have high flow, so they have more flow, and so they can have high velocity erosion, wasted energy. Obviously, if you're flowing more than what you need in a certain zone, you're wasting energy. You can have latent load issues where your flow is too high, and so you're not removing the humidity from the room. And then again, equipment malfunction, and the worst, increased number of callbacks. So in an unbalanced system, you are getting both high flow and low flow problems. And in those high flow and low flow problems, you can have them in the same system at the same time. Let's see, I have a chat. Someone's saying they're not getting any audio. Is everybody else getting audio? I just want to make sure.
Of the shaft.
Are you others getting audio? Type in if you are, so I can just make sure in the chat box if someone could. All right, great. So in an unbalanced system, there's high flow problems as well. So we want to talk about what makes these systems inherently out of balance. We know that they're out of balance because you've all experienced it enough in your careers where you know that the ones closest to the pump get more flow and the ones farthest. But why does that happen? Well, we want to talk first the most basic principle, and that is a very simple system with just 2 coils. Obviously, this could be carried out to be 50 coils, 100 coils, but we're going to go very simple with just 2 coils, so 2 zones. These coils are designed to have 10 gallons per minute, and we're not going to have any friction loss because friction loss is actually what is causing this unbalanced system. So we want to look at it in the ideal world where we have no friction loss. So if you've got no friction loss, your pump is over here on the left side, and you're pumping into this hydronic system. This is a standard direct return parallel circuit system. And so you're going to come to the first coil, and you're going to have 50 PSI coming out of that pump. And so that coil inlet is going to be 50 PSI in this first coil. Then the water will continue down to the next branch. And because there's no friction loss, that coil will also have an inlet of 50 PSI. And again, I said this is not real world. This is an extreme situation where we just want to show kind of the ideal where there's no friction. The coil has been designed for a 4 PSI drop across it. And so coming out of this second coil, we have 46 PSI. Well, we've got no friction loss, so that water that gets back to the outlet of the second coil also has 46 PSI. So in an ideal world where there's no piping losses, you've got the same inlet and outlet pressures across both coils. And so you've got the same coil design for coil 2 is the same as for coil 1 with the 4-pound drop. So your required flow is 10 GPM and you're maintaining 10 GPM. Now, obviously, like I said, this is an ideal world situation and not reality. In hydronic systems, this final coil here, the one that's furthest from the pump, is called the index circuit. So when a pump engine designer is putting together how large the pump is, they're going to just look at this one circuit right here, this index circuit, and that's how they will size their pump. So now we're going to move to a more normal circuit with friction loss in it. And in this normal circuit, we've got the same pump on the left side, 2 coils. the flow going through first to the first coil, and as well because it's parallel, flow going to the second coil. Now, the reason that you start to have an unbalanced system is because Bernoulli's equations dictate that the PSID across this one loop right here, so that's the first coil in our situation, the pressure drop across that full loop has to equal the pressure drop across the second loop. And if we carried this out and we had more than 2 coils, it would be the same thing. That's why when a pump is sizing, an engineer is sizing their pump, they're just looking at this one red index circuit. They're not adding up all of the valves, all of the strainers. They're just adding up what the pressure differential is across that index circuit. Because in Bernoulli's laws, the pressure differential across that red circuit has to equal the pressure differential across the yellow circuit. So in a hydronic system that's closed, where everything's in parallel, you're going to have the same pressure differential across each of those circuits. So that way you know what the full index circuit is. You can carry that back and look at other coils. So if we're looking at this now, our system, we've got 50 psi, just like before, coming into coil 1. Now we've got some pipe loss, some friction pipe loss of 4. So now coil 2 is now having a 46 psi drop. We're going to have 4 psi across the coil because typically they're sized for 3 to 5. And so we'll have a 42 psi outlet from coil 2. And then we've got more friction loss so that the first coil now has an outlet of 38 psi. Now again, because we know that the pressure differential across each branch has to be the same, we now know that that coil, the first coil, does not have a 4 psi drop. The difference between 50 and 38 is actually 12. So again, the coil is not creating pressure loss in the system. There's nothing in there to create more or less pressure loss. It's just a piece of pipe. And so because we know that the pressure drop in branch 1 versus branch 2 versus they're all going to be the same, that's how we know that the coil pressure differential is going to be 12 psi. So if we use a CV calculation like we talked about last week, where this the GPM is equal to the CV times the square root of the pressure drop, so it's that same calculation we've used. Now we know that that first coil has a flow rate of 12.7 gallons per minute, and the second coil has a flow rate of 7.3 gallons per minute, and that's assuming that the CVs and the 2 coils are identical and everything is the same. So you can see the issue is the friction loss. So in any direct return system where you've got the Bernoulli's rules that say that the overall full circuit pressure drop in the index circuit has to equal the pressure drop in all the other circuits, you can see how the ones close to the pump, now those coils and any valves that are there, anything else, they're going to have more pressure differential. So intuitively you know that because this ones closest to the pump usually have more pressure differential, and the ones farthest from the pump usually have the least amount of pressure differential. So I think intuitively you get it, and you've seen it, but it's good to see how the friction loss impacts it. And so typically, let's say our coil here that was supposed to be at 10 is now at 7.3, and that building manager gets lots of complaints, and I'm not getting enough heating or cooling, I need more. So any building manager's first reaction is, well, let's just get more pressure, more flow. So they're going to try to increase the pressure by turning up the pump. And so here it shows that that does absolutely nothing to help the system. The exact same principles, which is the friction loss in the pipe, are absorbing some of the pressure differential on that index circuit. All of that piping loss is not impacted at all by the absolute pressure, right? It's all about the pressure differential. So the solution that many have, which is to just increase the pressure, doesn't make any difference at all. So we've talked about direct return, but I want to talk more specifically about direct return and reverse return. In reverse return, there's more piping. And so in a direct return system like we've looked at, you see how the friction loss of the pipe really does play into causing this unbalanced system. So we'll look at direct return and reverse return, because reverse return was a solution that somebody had at some point to add more friction loss from pipe. So we'll stick with the direct return though. And so now you can see I've increased the system. Now we've got more coils, 5 coils in the system, and we have different friction losses in the pipe. But really the goal here is to show that we have the exact same problem. The index circuit, the circuit pressure drop for the index circuit equals the circuit pressure drop for the first circuit. And so therefore, because there's all that friction loss in the piping to get to that index coil, you don't have as much pressure available in the index coil branch. And so you're going to have less pressure differential in that index coil than in any of the other coils. And so if you use the same CV calculations, GPM equals a CV times the square root of the pressure differential, you can see that the flow rate at that index coil is now 6.8. So again, we were still wanting 10 gallons per minute, but now we're at 6.8 on that one that's the farthest away. And you can see the one that's the closest to the pump has the most pressure differential, 24. And so now you've got a gallon per minute of 14.1. So the unbalanced system really starts out with the problem because of all that piping and friction losses. So this is a direct return system without any kind of balancing valve, and so you can see how the flow is impacted. So to prevent short circuiting, Johnson Controls in their Building Environments HVAC system book recommends balancing valves placed at every intersection along the supply path, maintain proper flow into the terminal unit and along the supply line. This is important because Johnson Controls, they're not a balancing company. We're a balancing company. They're typically an actuated valve and control system and all the other things that they do. So they acknowledge that to prevent that short circuiting that occurs in this index circuit where it's not getting enough flow, there needs to be some kind of balancing valve installed there. So if you use an automatic flow limiting valve, now we have installed on each coil an automatic flow limiting valve. And so regardless of the pressure differential, it's going to maintain 10 gallons per minute. And this is important because you can see, again, we had a circuit pressure drop across this portion of 26. Here we had 18. Here we had 12. So we have a different pressure differential across that coil and that pipe section. And so it's much higher, closer to the pump. And so by having an automatic flow limiting cartridge in there, it's going to maintain the constant flow of 10 gallons per minute, regardless of any other pressure changes, regardless of any other situations with actuated valves. So, like we talked about direct return versus reverse return, we talked about the piping is really the beginning of the problem. Johnson Controls in their book says the piping arrangement introduces a problem. In this design, most of the water flows into the first coil and then back to the return line. So as we talked about here, where we've got 14.1 gallons per minute, it's very accepted in our industry that in a direct return system without any balancing, you're going to have overflow in this first coil and underflow here. And like I said, this relates exactly to domestic hot water as well. We just did an application tip a few weeks ago for all of you that talked about this exact problem in balancing is also not just in hydronic systems, but in domestic systems where you have too much flow in some areas and not enough flow in other areas. So the solution that people came up with, because again, piping and friction is the problem and it's what's causing it. If you don't want to use balancing valves, another solution would be reverse return. So if you're looking at this piping scenario, you can see we've got an extra piece of pipe right here. So in a reverse return, the water comes into the first coil. When it leaves the first coil, it has a long run of piping to the end of the system, and then it goes back. And the goal, again, in reverse return, was to make those piping friction losses equalized throughout so that the zone that's closest to the pump does not get the most flow and pressure because it doesn't have friction losses. So their goal was to make the friction loss from pipe be identical for each zone. And it does somewhat help solve the problem. You can see here, now we've got 11.7. I think our worst case was 14.1 in the direct return. Our lowest flow is 8.3. Our worst case before was 6.8. So it is an improvement. But you can see that the way the pipe is, with pipe coming in and then going out and running all the way, the pipe length is considerably larger in a reverse return system. And you still have the same issues with friction loss, where, yeah, we don't have 24 PSI across any of these, but we still have more pressure differential and less pressure differential based on how the friction is distributed throughout the system. So yes, it is definitely closer to a better situation where you're closer to your 10 gallons per minute. But it does have, one, the increased expense of all the piping. And I know reverse return in general is not practiced anymore, but there are still territories and places where they are using reverse return. So because of that, we still want to talk about it. And it was a creative solution for how to address the piping situations problems. Reverse return was talked about not needing any kind of balancing valves. And you can see even a reverse return system benefits from having a balancing valve maintaining the flow at 10 GPM at all times. So a reverse return system can still benefit from that. Now, an ideal system has some kind of actuated valves. And so we make actuated valves. Our Training Tuesday next week focuses on those actuated valves. But a typical system is not just a coil with maybe a balancing valve. Typically, there is an actuated valve. And so in this system here, we've added in the actuated valves. This is back to a direct return system. So our pipe goes in and goes out. We don't have that extra piece of piping in. So we're back to the more normal direct return system. And you can see we've got an actuated valve on each coil. There is no balancing on this image, so this is just an actuated valve. And so just like the ones without any valves, you can see that our circuit pressure drop is anywhere from 27 on the one closest. And by circuit, I don't mean the full circuit where we have equal pressure drops across each section. I mean just this portion where it leaves the main and goes back to the return. So just this one section, we have a 27-pound drop down to a 7-pound drop. So because, again, we want that full branch to have an equal pressure drop here as it does for the index circuit, that's why we have so much excess pressure drop in the circuit closest to the pump. So because we have 27 and we have a two-way valve taking pressure drop in a coil, we have 20 pounds extra pressure differential. So across that coil, we're going to have 13.8 gallons per minute if we assume all the coils have identical CVs, down to the index circuit having 7 gallons per minute. So we still have the same situation where we've got too much flow close to the pump and not enough flow at the extreme distance, the index circuit farthest from the pump. And so typically in an hydronic system, what will happen is someone or something in the zone closest to the pump is going to either feel too hot or too cold because they're getting too much heating or cooling. Remember, they only wanted 10 gallons per minute by design for normal load. And so that actuated valve is going to get a signal from either the thermostat on the wall or a signal from the control system that says there's too much heating or cooling here. You need to modulate closed more. And so the system that has no balancing valves, those actuated valves are just going to be cycling repeatedly until they try to bring that flow into 10 gallons per minute. It will be a process that will never stop, primarily because as this coil here is modulating closed, it's impacting the pressure differential in all of the other branches, because as it's modulating closed, it's absorbing more pressure differential. So as it's changing the pressure differential, now the other branches have been changed. And so these actuated valves are going to do the work of trying to balance the system, but it's going to be a constant work where they're constantly cycling and moving and rotating open and closed to try to bring that flow always into the 10 gallon per minute range, basically into the design range. And eventually they could get there until someone changes some situation in the building, whether it's the sun's come up, more lights are on, and then the whole process starts again. So that's why I said they're trying to balance the system and bring the coil the flow that it needs at all times, but it's going to be an ongoing, continuing process of cycling to try to do that. So that's why that Johnson Controls quote about balancing and short circuiting that we talked about, to prevent the short circuiting, balancing valves placed at every intersection along the supply path maintain proper flow. So Johnson, who makes actuated valves, recognizes that ideally you want to take this system here with an actuated valve and add some kind of balancing valve, some kind of automatic balancing valve, so that now you can see we're at the 10 gallon per minute across the board for all of the coils. So the coil farthest from the pump has the flow that it needs, and the coil closest to the pump has the flow that it needs. So the solution, even in most actuated valve manufacturers' minds, is to add balancing valves. Now, this brings up the main question that people always ask, and we get asked this at Griswold quite a bit, and that is, well, how do the modulating valve and the automatic flow limiting valve work together? Are they fighting each other, is what they like to ask. And we get this all the time at Griswold, and I'm sure you do as well. And we like to say they're not fighting each other, they're cooperating with each other. Each valve has a purpose. So a modulating valve, its goal is to modulate from some design flow down to fully closed. And so it's going to modulate, say, let's just use our 10 gallons per minute that we've talked about. It's going to modulate from 10 gallons per minute down to fully closed, and it will control the flow in that area. Now, that's in an ideal world. In the real world, and I can say this because I also manufacture actuated valves, so I can tell you the truth from the actuated valve side of the world. An engineer is going to figure out they want 10 gallons per minute with a certain pressure drop. They're going to run that calculation like I showed you in the last presentation, and they're going to figure out what CV they want. Then they'll go to any actuated valve manufacturer's literature, and they will try to find a actuated valve that has a CV that makes it so they can have 10 gallons per minute across the valve at design load. Well, for us and for everyone else, we don't have infinite CVs out there. They don't exist. So the engineer is going to have to pick a CV that's a little bit higher. So now we already know that that modulating valve is now not going to work where the fully open is at design 10 gallon per minute. They have had to pick something higher. Maybe at full open it's 11 gallons per minute. Maybe it's 11.5. So at design condition, it's automatically going to be oversized. And nobody in the industry disagrees with that, because we all know that that's the case. Very rarely will you get the exact CV that you need. It does happen sometimes, but in general it doesn't. So that modulating valve, its goal is to modulate from 10 gallons per minute down to fully closed. But we know the control system doesn't really know what the flow is. So the control system just knows open more, close more, open more, close more. So as there's a need for more cooling or more heating, it will open more, and it will, at times during the day, open to fully open. So now we're in an overflow condition. So when the actuated valve is modulating below full load, that actuated valve right here has the authority. And the flow limiting cartridge, this is a small version of the graph we looked at last week. This is our flow limiting cartridge. And you can see our flow limiting cartridge doesn't start to control at 10 GPM until the pressure differential hits the minimum pressure differential in our range. So for a 1 to 14, this is about 1 PSID right here, and this would be about 14. So below flow of 10 GPM, that modulating valve is controlling the flow. Our cartridge is fully open. There's no pressure differential really across our cartridge because you're controlling the flow with the modulating valve at 5 GPM, 6 GPM, 7 GPM, all those reduced flow settings. So that modulating valve is in this range here controlling the system, while our cartridge is just a fully open, basically a hole in the pipe, just a fixed CV, and it's not compressed or doing any kind of action or activity in controlling the flow. This makes sense from an authority standpoint because for those of you that size control valves, you know that whoever's controlling the flow is the one that has the most pressure drop. So here, this flow limiting valve is about 1 pound, and the modulating valve by design should be 3 to 5 for modulating. And that pressure differential is actually going to be higher as that valve closes. So it's 3 to 5 at 10 GPM, but as it drops to 6 GPM and 5 GPM, it'll have 10 PSI across it, 12. So right there, the highest pressure drop has the control. It has what's called the valve authority. So it's controlling the flow below 10 GPM. When this control valve is either open all the way, so that sometimes happens or usually happens during early morning startup. It also happens anytime it's oversized, which again, like I said, is happening all the time in all of these systems. Now this valve is fully open, and so its pressure differential is actually dropping. Remember, it wanted 3 to 5 pounds at 10 GPM, but now it's fully open or it's oversized. So now its pressure differential is dropping to 2 to 1. It's getting smaller and smaller. And so there's more pressure differential available for our cartridge. And so our cartridge starts to compress, and that's the spring inside. It starts to compress and change this open area. So now our cartridge is controlling the flow to plus or minus 5% at 10 gallons per minute. So this is why we say they cooperate. When this valve is modulating fully open or it's oversized, so it's open more than it needs to be, the cartridge is controlling the flow, and that's this portion of the graph. But when the actuated valve is modulating to some reduced condition, usually because the load has changed and they don't need as much heating or cooling, our cartridge is fully open and not doing anything. So you really get the protection of balancing to make sure that you're always getting the 10 gallon per minute and never exceeding it. And that is important because when we look at this graph here with an actuated valve, you can see that we are exceeding it 13.8 just by the design of the actuated valve. So we don't believe that they are fighting each other. We say that they're cooperating because in a modulating condition now, if you're looking at this graph of the zones, this actuated valve here on all these branches, it will control the flow below 10 gallons per minute. So that is the summary of why system balancing is important. And I know that talking about Bernoulli's equation, those kind of things seem somewhat crazy, but it really does help explain why the system, the coils closer to the pump have so much flow and pressure, and the circuits farthest from the pump have so little flow and pressure. I hear a lot of time people saying, water, it takes the path of least resistance and that kind of thing. But actually now you guys all know better than those people that say water takes the path of least resistance, that the resistance, according to Bernoulli, in each circuit is exactly identical. So water sitting at this point in the system is not thinking, oh, I should just go here because that's the fastest way back to the pump. That's not true, because you can see that the pressure drop across this branch is identical to if the water had left here and gone all the way through that piping, all the way here, all the way back. So the pressure drop from here to here across the coil is identical to the pressure drop from right here where the water is also going in the parallel circuit to move on to the next coils. So the path of least resistance, it works in an open system. You can make that argument like we talked about in the domestic water application tip we did. There is a path of least resistance. But in a closed system hydronically, there is no path of least resistance. And really, the only reason that there's more pressure differential here across this coil is because there aren't all of the piping friction losses that go to all the other coils. So like I said, this is my favorite of all of the presentations because Griswold Controls, David Griswold created the balancing valve in 1960. And this is what we do at Griswold. We love automatic flow limiting. And so this is something that's in the heart of all of us. So we're excited to share it with you. And I thank you for joining us. I'm going to go ahead and open it up for any questions. If anyone has any, you can type them in the chat, or I will unmute so that people can ask questions. And if not, we have our third Training Tuesday next week, which is talking about actuated valves. And we will go into how to size actuated valves, the different types of actuators, the different types of actuated valves that are on the market. So we're excited about that. So join us next Tuesday, and appreciate you guys taking the time today to join us. Have a great day.